Okay. Good morning to all of you. In the last lecture of multiple integration, we have discussed the double integration and change of order to find the double integration. Now today's lecture of multiple integration will discuss about the triple integrations, its application and change of variable method to use the evaluation of multiple integration. First we take quick review of the lectures. Just look at the contents. Introduction, second triple integration, definition of triple integration, and the third part we'll discuss the change of variable method using Jacobian to evaluate the multiple integration, and at the last we will discuss the application of multiple integrations. Here we will discuss two particular applications of multiple integration, area and volume. Introductions. As we define single integration for function of one variable and double integration for function of two variables. Similarly, here we are going to define triple integration of functions of three variables. Let us first deal with simplest case where function f is defined on a rectangular box. The rectangular box R is x, y, z, a less than equal to x less than equal to b. The range of y is c less than equal to y less than equal to d, and z lies between r and s. The first step is to divide R into sub boxes. We do this by dividing interval AB into n subintervals xi minus 1 xi of equal width. Similarly, we will dividing the CD interval in m subintervals yj minus yj minus yj with equal width delta y, dividing interval rs into dividing interval rs, close interval rs into n subintervals zi minus 1 to zi with equal width del z. The planes through the end points of these subintervals at these intervals parallel to the coordinate planes divide the box R into L, M and sub boxes. That means this rectangular box R is now divided into sub rectangles number of L, M, N, and each rectangle box Rijk, the Rijk box equal to interval xi minus close interval xi minus 1 xi2 yi minus yj minus 1 yj to zk minus 1 gk. Each box has volume delta vik equal to delta xi, delta yj and delta zk. This way we have divided the rectangular box into LMN number of sub rectangular box. Just look at the geometry of the process. Here this box is rectangular box R. Now it is divided into equal sub rectangular boxes. Here we have mentioned two planes, one is xy and second on xz, which intersect, and after the intersection of this plane, at the intersection of this plane, we have one box, rectangular box, and that rectangular box is Rij, and this whole rectangular box is divided into small rectangular box Rijk. Next, as we have defined double Riemann sum for the double integrations, similarly here we are defining triple Riemann sum for the function of three variables. In this way, the Riemannian sum as ML equal to sigma I equal to 1 to n, j equal to 1 to m, and k equal to 1 to l, where xi dash yj dash zk dash del v ijk, where f of xi dash yj dash zk dash is in Rijk, the rectangular box Rijk is a point from value of function in the Rijk, and the limit of this SML, the Riemannian sum, is formally called triple integrals. Is formally called the triple integration. This way, we have find the volume of rectangular box by using the triple integration. Now, formal definition of triple integration is limit the triple integration of function xyz over the region R is triple integration f of xyz dv equal to limit n ml tends to infinity and summation I equal to 1 to n, j equal to 1 to m, and summation k equal to 1 to n for the function fx I yj zk in the volume delta vijk. Okay, next. After formal definition of integral, we have one practical approach to representing triple integration, and in the practical approach, the notation is triple integration f of xyz dv equal to triple integration f of xyz dx dy dz, where dx represent that first internal integration represent the limits of dx, the second integration middle integration represent the limits of middle variable dy, and the last outer integration represent the limits of dz. That means to evaluate the triple integration, we must have to remember this order, that is internal integration gives the limit of internal variable. Just here internal integration is a limits of dx, and similarly for dy, and outer variable has an outer integration limit dz. Next, we start with some example of triple integrations. Evaluate triple integration x y z square dx dy dz, where R is a rectangular box. On the table, integration triple integration R, the integrand is dxyz square dx dy dz, dx dy dz. Here R is a rectangular box with boundary x, y, z such that 0 less than equal to x less than equal to 1, minus 1 less than equal to y less than equal to 2, and the boundary of z is 0 less than equal to z less than equal to 3, less than equal to 3. Okay. as we have mentioned that the order of integration is important to evaluate the integration. In our integration, in our example, the order of integration is dx, dy and dz. That's why this internal integration has the value of variable x, and in our rectangular box the value of variable x is 0 to 1. That's why this integration, internal integration, has value 0 to 1. Clear? For the second variable y, the limits of second variable y is minus 1 to 2, minus 1 to 2, and limits of third variable z is 0 to 2, 0 to 3, is 0 to 3, equal to, once we get the limit of integrations, then we will try to evaluate this integration. First we integrate integral integration x y z square with respect to dx dy dz. Okay. Now for the internal integration minus 1 to 2, for this integration, here we are integrating the integrand with respect to x. That's why this y and z are taken as a constant. So integration is y z square, and integration of x is x square by 2. Evaluate this bracket between the limit minus 1 to 2 dy dz, dy dz, 0 to 3 minus 1 to 2 yz square. Substituting limits of the integration, that means we get 4 by 2 minus 1 by 2 dy dz is equal to, result is 1 by 2, this 2 minus 1 by 2 is 3 by 2, 2 minus 1 by 2 is 3 by 2, integration 0 to 3. Here second integration is minus 1 to 2 yz square with respect to dy dz. As we have done in the case of x, here we are integrating with respect to y. That's why z square is constant, and 3 by 2, 0 to 3 z square minus 1 to 2 integration of y dy dz, y dy dz, y dy. Continue the process. 3 by 2, 0 to 3, 0 to 3 z square, integration of y is y square by 2. Evaluate between the limit minus 1 to 2 dz. 3 by 2, 0 to 3 z square is equal to 4 by 2 minus 1 by 2 minus 1 by 2 dz. That's why limit is 3 by 2, 2 minus 1 by 2 is 3 by 2, integration 0 to 3 z square dz, z square dz. 9 by 4, integration of z square is z cube by 3, 0 to 3, and value of this integration is 9 by 4 into 27 by 3 is equal to 81 by 4. Result is 81 by 4. That means here this way we have simply integrate the triple integration on the rectangular region. Now next part, in the next example, evaluate triple integration over the region R z dz dy dx, where R is enclosed by the plane x equal to 0, y equal to 0. The region R is not rectangular box, but it is bounded by 4 planes x equal to 0, y equal to 0, z equal to 0, and the fourth plane is x plus y plus z equal to 1. First we will try to develop the geometry of the region R. Just look at here. The first plane is z equal to 0. Z equal to 0. Now we have second plane x equal to 0. The green boundary is a boundary of z is equal to y equal to 0, x equal to 0 plane, x equal to 0 plane, and the blue boundary is a boundary of plane y equal to 0, and the brown boundary is a boundary of the plane x plus y plus z equal to 1. After the integration of these three planes, the resultant curve is represented by purple lines, which is a tetrahedron with 4 planes x z equal to 0, x equal to 0, y equal to 0,